Hi everyone, welcome. There's lots of space up at the front if you're cramped in the back there. My name is Indigo Esmond and I'm a faculty member here at OISE, and I'm very pleased to welcome you all here and to welcome Joe Boaler on behalf of the OISE Visiting Scholars Program and the Department of Curriculum, Teaching and Learning and the OISE Center for Science, Mathematics and Technology Education. We're very excited that Dr. Joe Boaler is here to talk with us today. She is a professor at Stanford University in the School of Education. She's also taught at King's College in London and at the University of Sussex. She was a classroom teacher in London Comprehensive School, so she has a wealth of experience in teaching and teacher education and in research. Her research is award-winning, most recently with the Equity Award from the National Council of Teachers of Mathematics, which, if you're not familiar with it, it's a US and Canada-based organization to promote effective math instruction. Jo has worked with teachers all over the US and, in fact, all over the world. Last year, she taught a massive open online course called How to Learn Math with 40,000 students. It was a really fascinating course. I enrolled, and I know that there are some folks in the audience who took that course. It helped teachers and parents gain insight into what learning math could look like if we approached it differently, drawing on insights from research in education, cognitive science, neuroscience, and psychology. Jo is in very high demand as a speaker. She's speaking this week as a plenary speaker at the Ontario Association for Mathematics Education. It's tomorrow morning at Humber College. And she was also recently at the White House working with a panel on gender inequities in science, technology, engineering, and mathematics education. So we're very pleased to have Jo here today for her talk entitled Beautiful Math. Maths.
Thanks, Indigo. It's great to be here. And I'm just going to start in with some hard facts and tell you that maths actually is the subject with the greatest difference between what we know works from research and what happens in classrooms. So we actually have decades of research telling us about good mathematics approaches that work really well, that haven't really found their way into the system well. It's also the subject with the greatest difference between the way school children would define it and the way experts define it. If you ask a mathematician what math is, they'll usually tell you it's the study of patterns, it's this very beautiful aesthetic subject. That's not what school kids say, as you probably know, if you ask them what math is. And it's the subject that should be one of the most useful for their lives. Yet even where students study hard in classrooms, the knowledge they get is often unuseful. And I'll show you a bit more about that later. So a little pop quiz for you before we go on. What's the connection between maths or math and broccoli, do you think? You can just think about this for a bit. So if you're a math teacher, you're probably thinking about florets and Fibonacci and all sorts of things. Actually, the connection I want to share with you is from a survey very recently that told us that over half of middle school students in the US said they would rather eat broccoli than do math. 44% said they would rather take out the trash. So we know it's not very popular and there's widespread underachievement. So I wanted to talk to you about why that is, and we're going to look inside some classrooms together and really see what the difference is between really successful and unsuccessful math teaching. So I'm going to talk about two big things today. I'm going to talk about the beliefs and messages about math that are around, and I want to talk to you about multi-dimensional mathematics and its converse, which is one-dimensional math. So I wrote a book for teachers and parents a couple of years ago. The one on the left is the US version, What's Math Got to Do with It? In England, we called it The Elephant in the Classroom. It's really a similar book with different spellings, but different examples of classrooms and some other things. But I called it that name, The Elephant in the Classroom, because I argued in the book that there's a big elephant standing in most math classrooms. So you know the expression, the elephant in the room, which is an idea everybody knows about but nobody really talks about. And the elephant that's standing in most math classrooms is the idea that only some kids can be good at math. Turns out teachers believe that, students believe it, parents believe it, And that single idea is the cause of a lot of the problems we see in math education. Ever since I wrote that book, people have been sending me photos of elephants in classrooms. I'm not sure why. This was a London one I got. But in contrast to that, I'm giving a talk tomorrow on mathematics and mindset, and I'm not going to give you that presentation today, but I do want to mention a couple of things. So there's a widespread myth out there that math is some sort of a gift that some people have and some people don't. There is no evidence for that at all. In fact, there's a wealth of research that contradicts that. There is no math gift. There is nobody born without a math gift or with a math gift. And in fact, the new evidence we're getting from studies of the brain tells us that every child can excel in math to all levels of high school and beyond, but at least to the end of K-12 education. And you may think about kids who seem slower or don't know things. That's because of the experiences they've had. It's not to do with some genetic brain things. So this is really important evidence, and it's really important that we pay attention to it. Turns out it's also really important how kids themselves think about their own ability. So could you put your hand up for me if you've heard of Carol Dweck and mindset? So she's a Stanford professor, and she wrote a book which became a New York Times bestseller. And in it, she explains that there are two mindsets that we all have. You have them, I have them, everybody has a mindset. And some people have what's called a growth mindset, where they believe that the more work you do, the smarter you get. Some people have a fixed mindset, where they believe that you're either smart or you're not. So it may be that you have a growth mindset in relation to lots of things in your life, like you might think, the harder you work at soccer, the better you'll get, or the harder you work at cooking. But in math, you can either do it or you can't. So there's a lot of fixed mindset thinking about math. Turns out these mindsets have a huge impact on learning and achievement. And this is right. Kids with a growth mindset, those who will persist longer, who are happy and willing to learn from mistakes, they're determined to keep going, they're encouraged by others. Kids with a fixed mindset, and the teachers here will recognize these kids, are the ones in classrooms where you give them something a little more open or challenging, and they'll immediately say, I can't do this, and can I have help? So we know that fixed mindset thinking affects students from across the achievement spectrum. In fact, it's particularly present in high-achieving girls, and I'll say more about that. And that was what I was talking about a lot of at the White House. And we also know that parents are key in the mindset kids have, parents and teachers, because kids get a fixed mindset by hearing something you hear a lot in the US, probably here too, which is parents telling their kids that they're smart. So in the US and other countries, when kids do things well, parents will constantly say, oh, you're so smart, you're so smart. So now we know that what happens when parents say that is the child thinks, oh, I'm smart, that's good. But then later when they fail, and they do, they think, I'm not so smart. So in Carol's latest research, they found that the praise parents and others gave their babies between the age of 0 and 3 completely predicted mindset 5 years later. So this is very important that we change the way, and we praise people for learning and growth, replacing with, oh, you're so smart, with, wow, you've learned that, that's really great. This graph just shows you they gave a survey to kids, followed them over 2 years, and they just looked at their achievement, and the survey found out what mindset they had. So the bottom line is the kids with a fixed mindset whose achievement just goes along. And the kids with a growth mindset are those who go onwards and upwards and achieve more and more. I'm working with the PISA team. I know the PISA tests, the international team that do tests across the world, have been gaining a lot of attention here in Canada and in Ontario. But the PISA team not only collect math scores, they also look at kids' mindset, and they also find out about the kind of strategies they use. So it turns out the lowest achieving kids in the world are what they call memorizers. So the kids with a memorization strategy go through math thinking they have to remember lots of things. When they approach a test, they'll say, I prepare for a test by trying to memorize the methods. Those kids are the lowest achieving. The highest achieving kids are those who go in and think about the big idea, who prepare by thinking, what's the main idea here? So they're approaching math a lot more conceptually. So this data comes from 13 million 15-year-olds, all of the PISA kids across the world, and it shows what they found was a huge difference between those with a fixed mindset, as you can see, and a growth mindset. Years of math separated them in terms of their achievement. And the kids who are the very highest achieving in the world are the kids with a growth mindset who also have positive math strategies, who see math more conceptually. So this is all part of telling you how important it is. If you want to read a little more about it, this was an article I wrote for The Atlantic, which is very easy to find online if you just Google my name at The Atlantic, and it describes a bit more detail on this and gives you some references. So I want to talk to you now about the nature of the math we teach in classrooms. It turns out most of the mathematics that's taught in schools right now is over 400 years old and is actually not the mathematics that students need. So we really need a revolution in the math that's taught. But the other problem is the mathematics that's taught now, particularly in high schools or secondary schools, is what we would call one-dimensional math. So teachers explain a method, kids copy and practice. There's really one way to be successful. Some students are successful doing that, others aren't. Some students can do it, but it's not very interesting, so they disengage. That's one-dimensional math. When teachers teach multi-dimensional math, they say, well, getting procedures, working through procedures is one way of being mathematical, but there are many ways of being mathematical. A mathematician, for example, if you look at how a mathematician works, she will start by asking a question. That's always the way to start, asking an interesting question. But then also they need to problem solve, they need to communicate with different graphs and drawings and words. They're representing things in many different ways, and they're reasoning. So multidimensional math is the math that mathematicians use, and it is the math that's needed in the world. Uni one-dimensional math is very different. It's actually a very narrow version of what mathematics is, and it's a version of math that's pretty antiquated. So I'm going to let you listen now to one of the leaders in the high-tech world talk about this, and this comes from a TED Talk. So Conrad Wolfram is the CEO of a huge mathematics company, one of the biggest in the world, called Wolfram Alpha. If you don't know Wolfram Alpha, it's great. You can ask it any math question and it will come back with not only an answer, but different representations of the answer. It's really great. And they also own Mathematica, very, very big worldwide math company. And Conrad Wolfram is trying to change math education. So we're going to listen to just a few minutes of his TED Talk that he gave in England a while ago. And let's hear his point about this.
We've got a real problem with math education right now. Basically, no one's very happy. Those learning it think it's disconnected, uninteresting, and hard. Those trying to employ them think they don't know enough. Governments realize that it's a big deal for our economies, but don't know how to fix it. And teachers are also frustrated. Yet math is more important to the world than any point in human history. So at one end, we've got falling interest in education in math, and at the other end, we've got a more mathematical world, a more quantitative world than we ever have had. See, in the real world, math isn't necessarily done by mathematicians. It's done by geologists, engineers, biologists, all sorts of different people, modeling and simulation. It's actually very popular. But in education, it looks very different. Dumbed down problems, lots of calculating, mostly by hand. Lots of things that seem simple and not difficult like in the real world, except if you're learning it. And another thing about math. Math sometimes looks like math, like in this example here. And sometimes it doesn't, like, am I drunk? And then you get an answer that's quantitative in the modern world. You wouldn't have expected that a few years back. But now you can find out all about, unfortunately my weight is a little higher than that, but all about what happens. So let's zoom out a bit and ask, why are we teaching people math? What's the point of teaching people math? And in particular, why are we teaching them math? And in general, why is it such an important part of education as a sort of compulsory subject? Well, I think there are about 3 reasons. Technical jobs, so critical to the development of our economies. What I call everyday living. You know, to function in the world today, you've got to be pretty quantitative, much more so than a few years ago. You know, figuring out your mortgages, being skeptical of government statistics, those kinds of things. And thirdly, what I would call, you know, something like logical mind training, logical thinking. Over the years, we've put so much in society into being able to process and think logically. It's part of human society. It's very important to learn that. Math is a great way to do that. So let's ask another question. What is math? What do we mean when we say we're doing math or educating people to do math? Well, I think it's about 4 steps, roughly speaking. Starting with posing the right question. What is it that we want to ask? What is it we're trying to find out here? And this is the thing most screwed up in the outside world, beyond virtually any other part of doing math. People ask the wrong question, and surprisingly enough, they get the wrong answer, for that reason, if not for others. So the next thing is take that problem and turn it from a real-world problem into a sort of math problem. That's stage 2. Once you've done that, then there's the computation step. Turn it from that into some answer in a mathematical form. And of course, math's very powerful at doing that. And then finally, turn it back to the real world. Did it answer the question? And also verify it, crucial step. Now here's the crazy thing right now. In math education, we're spending about perhaps 80% of the time teaching people to do step 3 by hand. Yet that's the one step computers can do better than any human after years of practice. Instead, we ought to be using computers to do step 3, and using the students to spend much more effort on learning how to do steps 1, 2, and 4, conceptualizing problems, applying them, getting the teacher to run them through how to do that. See, crucial point here, math is not equal to calculating. Math is a much broader subject than calculating.
So Conrad Wolfram's not the only person who's trying to raise awareness of this. I work with a lot of people in Silicon Valley. Stanford University is situated right in the midst of that. And I've been realizing that the leaders in Silicon Valley are all very unhappy with this sort of antiquated traditional math that's being taught. In fact, the leader of Google, you might have read, publicly said that they're no longer going to look at test scores or achievement data when they employ people at Google because it has no correlation at all with how well they do in the company. But they're particularly critical of math. Here's one of the people. Sebastian Thrun is a very accomplished person. He's the CEO of Udacity. He invented self-driving cars as a Stanford professor. He's a VP at Google, and he led the team developing Google Glass and many other things, so he's a pretty high achiever. And this is Sebastian talking about math. He says, for many kids, math provokes an allergic reaction, yet it is perhaps the single most important skill to have if you want to find a job in Silicon Valley. To me, maths is all about problem solving, reasoning, using intuition, and making connections. It's not about memorizing formulas. So it's very important that we move beyond this one-dimensional math that's in classrooms. Apart from anything, it's very boring for kids. They disengage, they opt out of mathematics. But multidimensional math also opens the door to many more kids. It turns out when you teach a broader mathematics, many different students can engage with it. When you teach a narrow mathematics, there's only a small group of kids who are suited to that kind of approach. And multidimensional math is the math that's needed in the world. So I thought I'd show you a little bit of what I mean by this by taking you inside a classroom. We know from many different studies, many studies, that when math is taught in this traditional way and it's experimentally compared with same kids who go through different teaching approaches, the kids who go through what we might call inquiry-based mathematics or multidimensional mathematics achieve at higher levels, they participate more, and they go on to more math classes, and it's more equitable. So I'm going to show you, just to illustrate from a study, there was a study conducted of 700 high schoolers in California going through different mathematics approaches. the traditional math approach that you probably recognize and know well, and a multi-dimensional approach. And we're going to, as I said, step inside the classrooms to see what that looks like. But before I take you into those, the kids were followed over 4 years, and the achievement at the beginning of the study, the kids doing the traditional math were also in more suburban schools, and they were at higher levels when the kids started high school. The kids in the multidimensional classes were in more urban settings, and they started at lower levels. By the end of the first year, they'd caught up, and by the end of the second year, they were significantly outperforming the kids who were learning in the traditional math classrooms. Also, they enjoyed mathematics a lot more. 47% of seniors in the multidimensional classes went on to, were in calculus classes, compared to only 23% of the kids who went through the traditional approach. So we have a lot of data and evidence on what works in mathematics classrooms. As I said, we don't see it that much, but let's have a look now. In one of the schools, they actually taught the traditional approach and the multi-dimensional approach side by side. And kids and parents could choose which one they wanted to do. So sort of almost perfect experimental conditions, really. And we were following kids through the different approaches. So we're going to, first of all, go into the traditional classroom, as labelled by the school. They called it traditional math. And my question for you as we watch this clip is, how are students engaging in math? So we're just going to watch a minute now, and let's see what you see.
Let's see, we want S minus A, and A happens to be a 3 here. And then we want to go S minus 4. And then we want to go S minus 5. And end it with a parenthesis. So on a separate piece of paper, I would like you to try these 3 problems. Done with notes? It's done with notes? Yeah, we're about to do some practice here.
How are those students engaging in math? What do you think? Passively? Anybody else? So, the next clip I'm going to make you talk about, so I'll get more things. But passively is probably a good description. This 1-minute clip, we had hundreds of hours of these kids working. They all looked exactly like this. We could have picked any 1-minute clip. And this probably may not be that dissimilar to your own secondary math experience. Put your hand up if you were in a class that looked like this. I'm not sure. Probably quite a few, not everyone. So we asked the kids the same question. We didn't say, how do you engage in math? But we asked them, what does it take to be successful in math class? And of all the hundreds of kids, a stunning 97% of them said the same thing. They said, you have to pay careful attention. So we know that is a very passive learning activity of thinking. You just have to listen carefully. And not that helpful for kids. So now I'm going to take you down the corridor, same school, same age kids, and we're going to go into a multidimensional classroom. So the curriculum that's used here is called IMP, and it's a sort of more applied conceptual math curriculum. And this is the problem they're working on. So they've been told that a skateboarder is holding onto this spinning merry-go-round, and they let go at the 2 o'clock position. And at that time, they crash into the wall. And the question they're answering is, how long will it take the skateboarder to hit the wall? So resist working on that problem now on pieces of paper. I know you're dying to. But it's a pretty complex problem, involves different areas of math. And we're just going to see a minute from the classroom again. So what the teacher's done, though, is she's asked different kids to come up and present. But unlike a lot of teachers, usually with presentations, teachers have the kids work on something and then ask kids to present their results. And that doesn't always work that well, because somebody will go out and present, the other kids have already done it themselves, they're not that interested. So this teacher does something different. She asks the kids to work on the problem for a few minutes, and then before anyone solved it, she stops them. and then they end up solving it together. So we're just going to join them for a minute of class, and I have the same question for you. How are these students engaging in math?
Well, because it's not
Could you read?
Because it's perpendicular to this line,
Right.
and it's at the 2 o'clock point exactly where it's like tangent to the circle, right there. And so we can just take the 2 o'clock line and say that that's a perpendicular line to his release line. So now that we have that, we could come back to, I don't know, that picture's. We have this line right here, and so we have 90 here, and
Aren't those two triangles, that little triangle that's formed with a 30-degree angle and the big triangle, aren't they similar triangles? So aren't the sides...
Which one? Right here and this one?
Yeah.
I don't know. We could try to prove it.
They should be. They should be because they're cut with the same...
I say we should try to take the break.
Both the lines are parallel.
Good game.
Why wouldn't they be?
So that means, you know, like, you can find the,
Wait,
ratio
didn't you figure it out just
of
there?
the, like,
right
the small one to the big length, and that you can find the ratio of the two sides, and then you can use Pythagorean theorem to find the length.
Yeah.
This one would be 60 because 180 minus 30 minus
yeah,
90 is 60. And then this is a line, right? So this is 180 degrees.
Okay, so this time I'm going to ask you to talk to someone around you and tell me talk to each other about how those students engage with math. What are they doing? What are they actually doing in the classroom? All right, I'm going to get you to wrap up your discussion. Okay, now I'd really like to hear, we're just going to pretend we're a big class now at Stanford. What do people see? What do they see them doing in that math class? Anyone, just shout it out.
Talking.
Talking? Okay. Discussing? Participating? I'm going to write these down.
Problem solving.
Sorry?
Problem solving.
Mm-hmm. Problems.
Debating.
Mm-hmm.
Clarifying.
Clarifying, I missed the... Mapping, what was the building on?
Building on one another's ideas.
Uh-huh. So, as you can tell from the words you've used, these kids are engaging very differently in mathematics. And at the end of the 4 years, not only did they do better on traditional tests, but they really developed a much more positive relationship with math, where they saw it as a subject that they could actively use and engage with, and many of the verbs you're talking about. I don't think I have the slide up here, but when we asked them that same question, what does it take to be successful in math class, they came out with a whole range of different things. They said we have to ask questions, we have to talk to each other, we have to connect methods, we have to use ideas and drawings. So they saw math as much more, it was broader, and they saw it as broader. Some other things you can see in there. It's the students, not the teacher, solving the problem. You'd be surprised how rare that is in math classrooms. And the work is shared. So you see students listening to each other, building on each other's thinking. That's a very advanced mathematical communicative skill, to be able to listen and bring a mathematical idea to it and build on it. And it's very valuable in industry right now. You may have been noticed they were laughing, they were enjoying their work. And really importantly, they were using their own thoughts and ideas as well as formal mathematical methods. So they were choosing methods, applying them, bringing in their own thinking. It's a very different mathematical experience, and it's one that is associated with high achievement. But the students also talk about math differently. I started off by saying that students don't think about math in the way mathematicians do. Well, this is a quote from one of the boys. We asked them at the end. In fact, the boy at the board, Toby, this is him talking about math. He says, math is really beautiful, and it has these patterns in it that are amazing. Most art is just made of patterns anyway, and so I've written a lot of poems about it, and a lot of songs involving it. He's Californian, so... A lot of songs. Polyrhythms was one thing that kind of interspersed music and math for me, because it's like patterns that take multiple measures to repeat because they don't fit evenly over 4 bars, and it's like a fraction, because if you take a fraction high enough, there's going to be common denominators, and so seeing how patterns can be interspersed and artistic, and math intersperses a lot for me that way. So you may read this quote and go, wow, this kid's unusual. He was unusual because he actually was taught real mathematics. This is what math is, that most kids never even see, unfortunately, in K-12 classrooms. So this is the multidimensional piece. I want to also share with you today, 3 big ideas that are coming out of the really interesting brain research that we have, that I'm going to be talking more about tomorrow at tomorrow's conference. But one of them is this. I argue that it's actually very hard to develop and maintain a growth mindset about math if all you do in math class is answer short questions that are right or wrong. What that does for kids is they don't actually think math is about learning. They think math is about performing. So most students, if you ask them about what they're doing in math class, they think that they go into math class to get questions right. They think that they're going to go in, they're going to be asked questions, and they have to get them right. That's not a learning perspective, that's a performance perspective. And this really came home to me recently. Rachel Lambert, a colleague, told me that her 6-year-old son had come home from school that day and said he didn't like math. And she said, why? You know, what happened? And he said, math is too much answer time and not enough learning time. Which is pretty amazing from a 6-year-old, but he's right. They're already at 6, they're getting this perspective. I go into math class to answer questions. So what we need is to open up math tasks so that they have the space to learn inside them. If you see a math question and there's no space for kids to learn in it, then it's not a good math task. And you can do that in different ways. Encouraging different ways of seeing the problem, different methods and pathways through the problem, different representations of the problems. When math tasks are open, the opportunities for learning and for developing a growth mindset are increased. So tomorrow we have more time and I'm going to show people some tasks that are like this. But we need to change the curriculum in math classrooms in these ways. And then something really interesting that's coming from neuroscience is the message that math should never be associated with speed. And it's very interesting, this is coming out from the brain researchers. But what we now know is time tests, which are used all over the States, I hope not so much here, but cause the early onset of math anxiety. And if you want to read more about that, this is an article that just came out in the NCTM magazine that I wrote with the data on this and what we know about speed and math anxiety. And it's downloadable on YouCubed, which is a website which you have on a card, hopefully. And I'll tell you about, and it's on that site. But so this is the reason. We now know that when people work on mathematics, they hold math facts and math ideas everybody holds them in the working memory part of the brain. But what they are finding from watching people's brains when they work in different situations, and we now know, is that when you're stressed, your working memory is blocked completely. And you can't access the math facts. So you may have experienced this, I know I have. If ever you've been stressed by math, like you've had to do math publicly, or with somebody, watching, or any sort of stressful situation, and you suddenly feel like your mind's gone blank, like you just can't think of this math thing. That's the impact of stress hitting the working memory. So it turns out when we make speed a part of math classrooms, about 1/3 of kids get very anxious, and then they can't perform. So this is what starts math anxiety, because they feel that they can't do math. I'm very fond of sharing, I don't have it here, part of a memoir of a top mathematician. I work with mathematicians all the time. They're not fast math thinkers, contrary to public opinion. They're actually very slow math thinkers, and they think slowly and deeply about math. So there's a mathematician who wrote a great autobiography called Lawrence Schwartz. He won the Fields Medal for Mathematics. He's a top mathematician. And he wrote a biography about how he felt stupid through his school days because he was one of the slowest math thinkers. And he went on to win the Fields Medal. He probably wouldn't do that if he'd been in some classrooms. But we give kids the idea from an early age that if you're not fast, then you're not a math person. And we dissuade them from believing that they can be a math person. There is no relation between stress and prior achievement. You can be a high achiever and be just as stressed. And in fact, the research on timed tests shows that it is the high achievers who are most disadvantaged and have this blocking of the working memory. But we also know that math stress particularly affects girls. So it's really important that we dissociate math from speed in all sorts of ways. If you're a parent, don't use flashcards. Give kids, engaging math apps or tasks that let them go deeply into mathematics. So another big thing that's coming out of the brain research that I'm doing a lot with teachers these days is, so I teach workshops at Stanford and other places on how to teach math for a growth mindset. And Carol Dweck came into the first workshop and she shared something that made all the math teachers in the room go, and I also thought, wow, this is really significant. And what she shared was this. She said, every time a student makes a mistake in math, they grow a synapse. And since then, since the time she first said that, we have new brain research that shows that when you make a mistake in math, you have brain activity and growth. When you get work correct, no brain activity happens. So this is actually really significant because it means that mistakes are good. Now, good teachers have always said, we learn from mistakes are good, but this is different. That we actually need kids making mistakes. They're the time that your brain is growing, and that means we need them to be okay about it. Because students everywhere, as you probably know, hate making mistakes in math. And that's partly because they've been brought up in a performance culture, because when they make a mistake, they think, I'm not a math person. But we need them making mistakes, so we need to be giving them longer and more challenging work, and we need to change the culture and the way that they're positioned. So teachers can change it. I have great examples of how teachers share with kids this important evidence about mistakes, and they do great activities with kids, so they value mistakes, they encourage mistakes even, and talk to kids about why they're good, and parents can do it too. I have my own math traumatized daughter, actually, she's a work in progress, but she's 11, had some bad math experiences in the early years, and she's much better now. But I remember being in a situation where she got a question right and she got a question wrong in a math thing, and immediately she got the math question wrong. She went, I'm so bad at math, I can't do math. And I said, you know what just happened? When you got that work right, nothing happened in your brain, but when you got it wrong, there was brain growth. And she was like, it's a really important message. You don't have to go back and get the work right for that brain growth to happen. It's not about learning the math. It's actually about being challenged and being in a place of struggle in your brain. That's what causes brain growth. So the other thing that's really important, that's coming also from the brain evidence we have and psychological evidence, is just the power of messages we give to kids as parents, as teachers, particularly teachers. An amazing study, this is still my most ranked as the study I'm most amazed by, was done with huge numbers of kids in high school English classes, and they all wrote an essay and they all received diagnostic critical feedback, as they often did. And then for half the students, researchers attached a one-sentence note. One sentence, and the other half didn't get it. The kids who got that one sentence, with no other differences, achieved significantly better a year later. And the one sentence that they put on their work was this: I'm giving you this feedback because I believe in you. And the kids who received that message from their teachers achieved significantly better across a year. The teachers did not know who got that message, so it wasn't because of changes in the teachers. So we know that the messages we give kids are hugely important. We now know that they're probably more important than the math knowledge they have, is their ideas about their own belief. They're constantly sitting in classrooms processing, does my teacher believe in me? Is my teacher giving me that work because they think I can't do it? Are they Is my teacher speaking to me in that way because she thinks I can't do it? So these are really important for parents and teachers. So just before I finish, I want to share a couple of resources for you. Indigo mentioned I taught a MOOC last summer, which was a bit of an experiment for me, but I wanted to get these really key important ideas about the brain out to everyone. It was for teachers and parents, and it's open again. 40,000 people took it last summer, and the results were had much bigger impact than I ever thought. At the end, 92% of people said they were very or extremely satisfied on a big 7-point scale. 95% said they would change their teaching as a result of what they learned through the MOOC. So they changed their mindsets. A huge number of elementary teachers mainly that told me that, I have heard this word over and over again, that it was life-changing for them. And they will say that it's life-changing because it made them realize they could learn math. So there's sort of, anyway, that's available again now. Also on the card is the link to that. Stanford's now charging for that course, but only $125. I hope that. I'm hoping school districts will pay and schools will pay for teachers to keep doing that. But that's for teachers and parents were really happy about it too. So I'm very excited. I've now just finished one for students. So the idea of this is to get these key ideas straight to the students, and this time, the teacher one was 8 sessions of 15 minutes. This is 6 sessions. And it teaches kids these key ideas from the brain. Everyone can do math, that these messages that they probably have got at some point are wrong. But we also teach them that math is this very connected and useful subject. If half the teachers in the teacher course give this to their kids, it would go to 2 million students. So I'm really hoping this will have a big impact on, and if you know anyone, adult or child, this is really particularly designed, well, it will particularly help anyone who's struggled with math or has developed a kind of bad relationship with math. So I showed them in the White House a little clip, and I'll show it you. It's only a minute long from the course. And these are the sort of more gender pieces, but you'll see what the course is like.
When you make a mistake in math, your brain grows. Synapses fire in your brain. In fact, your brain grows when you make a mistake, but when you get work right, no brain growth happens.
Let's look at the brain evidence. Scientists now know that experiences grow your brain, and the brain is so plastic that it can rewire itself and grow in a really short space of time. In lots of stores, you will see aisles that are pink, meant for girls, and aisles that are blue, meant for boys. The blue ones, for boys, have building and construction toys that are really good for math.
So that's open now if people want to register or have students. I'm hoping that teachers will use it with classes of kids, so they could all do it for, I mean, my ideal would be no faster than once a week, that maybe they do the little 15-minute section and then talk about it as a class would be really good, but people can also do it individually. And then finally, I want to leave with you that after the teacher MOOC, so many people, teachers and parents, said, please, can you keep giving us more on this and more resources, that I launched this website with Kathy, who's a director of a school district, mathematics in a school district, and the two of us launched a site. This includes some more videos and other things. So on this site, this is what we have up there now is a kind of an alpha site. It's about to move inside Stanford and become a much bigger deal. But if you sign up now with your email address, you'll get access to the new site. So at the bottom of the page, if you go to this link and you go down, it will ask you to sign up with your email address. So that's also on the card. And finally, I'm going to share a 2-minute other clip with you. And this comes from, I'm now working with a filmmaker, which is really great to be able to work with filmmakers. And I don't know if you've heard of, she's a pretty successful filmmaker. She made Race to Nowhere, which was huge in the US, and it was a film about the pressure in the education system. Now she's working on a more upbeat film, which, but in the making of this film, she's found so many people really asking questions about math, that she's working on a small math film, and please don't film this with anything, this is still in the making. When she finishes it in the next month or so, they're going to release it to news channels, so you'll see it. But here's a little clip. So what this talks about is I've been working actually in depth with one school district in the past 2 years. I haven't done this before. A school district with a lot of kids failing math. And I've done a lot of work with the teachers to try and change what I've talked to you about. They've changed their messages to kids. They've become more inquiry-based. And amazing things are happening, and she's capturing this on the film. You can see some.
In the United States, people think people have a math gene. Either you're born with it or you're not. If you don't have it, then you just don't have it.
Teachers believe that, parents believe it, students believe it. And it's one of the reasons that we have such widespread math failure and math trauma in the States.
I hated math. I absolutely hated it. I felt like I was like a little, like I wasn't nothing. When I went into other classes, I was like, well, I'm already failing in that class. Why don't I just fail in these classes? I wouldn't really try, and I wouldn't push myself.
It's amazing how many teachers have said to girls, don't worry, you don't need to be good at math. Math isn't your thing. Don't worry about that. When kids get the idea that they're not a math person and they start this sort of downward trajectory, many careers are cut off from them. And this happens to a lot of women, unfortunately. Their career options shrink massively. So we have a situation now where most engineers and most people working in computer science are men.
I hated math, to be honest with you, when I was younger. I felt that I couldn't do the problems quickly, and I thought you had to do them really fast. I think a lot of students come in with some of the same ideas that I had as a middle school student. They think that if they make mistakes, that means that they're not smart. Working with Joe has been really helpful in breaking down those stereotypes.
So what do you mean when you said it's not working?
Wait, did you just add the
Can I borrow this really quick?
Yeah, and then shoot her question.
I have like a connection with math now, definitely. Like, it's like I'm open and I feel like alive, and like I'm definitely like more energetic. In science, we use math a lot, and I feel like when they bring up math subjects, I'm like, oh, I learned that already. I could be open to like learning new things.
Well, that's
we're trying to get multiple methods.
So we're trying to figure out.
All right, thanks everyone for coming. I'll leave us with one question that has inspired me in Joe's talk, which is, what would our math classrooms look like if we all truly believed that all of our students were capable of excelling? And so with that thought in mind, let's thank Joe one more time. And thank you all for being here.